Clump distribution attraction clumping may result either from individual organisms being attracted to each other, or individual organisms being attracted more to some patches within a range than they are to other patches. The net effect is that some parts of the range will have a large number of individuals, whereas others will contain few or none. Uniform distribution repulsion. A uniform distribution means that approximately the same distance may be found between individual organisms. Uniform distributions result from individual organisms actively repelling each other. Random distribution, minimal interaction, influence. A random distribution means that where individual organisms are found is only minimally influenced by interactions with other members of the same population, and random distributions are uncommon. Random spacing occurs in the absence of strong attractions or repulsions among individuals of a population. Note that both clumping and uniform distribution suggest that individual organisms are either interacting with one another, actively seeking each other out, or actively avoiding each other, or all competing with one another for the same limited resources, regardless of the overall population density, as in the case of clumping, which results from geographical patchiness. 4. Demographics. Clump distribution attraction clumping may result either from individual organisms being attracted to each other, or individual organisms being attracted more to some patches within a range than they are to other patches. The net effect is that some parts of the range will have a large number of individuals, whereas others will contain few or none. Uniform distribution repulsion. A uniform distribution means that approximately the same distance may be found between individual organisms. Uniform distributions result from individual organisms actively repelling each other. Random distribution, minimal interaction, influence. A random distribution means that where individual organisms are found is only minimally influenced by interactions with other members of the same population, and random distributions are uncommon. Random spacing occurs in the absence of strong attractions or repulsions among individuals of a population. Note that both clumping and uniform distributions suggest that individual organisms are either interacting with one another, actively seeking each other out, or actively avoiding each other, or all competing with one another for the same limited resources, regardless of the overall population density, as in the case of clumping, which results from geographical patchiness. 4. Demographics. A population's demographics are its vital statistics, particularly those statistics which can impact on present and future population size. Two statistics that are of particular import are a population's age structure and a population's sex ratio. Age structure. Age structure refers to the size of cohorts within a population. Parameters related to age structure include cohort. A cohort is a group of individuals all of whom have the same age. In a typical population, the size of cohorts will vary with age. For example, in a typical population, younger cohorts will be larger, i.e., more individuals per cohort than older cohorts, all else being equal. Natality birth rate. Natality rate is the number of offspring per female per unit time. There are two types of natality. Fecundity maximum, absolute or potential natality. It is theoretical maximum production of new individuals under ideal conditions when resources are not limited. The greater a population's fecundity, all else held constant, the faster a population will increase in size. Note that fecundity typically varies with the age of individuals. Ecological or realized natality. It refers to population increase under actual, existing specific conditions. This is also designated as fertility rate. Generation time. Generation time is simply the average span between the birth of individuals and the birth of their offspring. Other factors being equal, a shorter generation time will result in faster population growth. Note that species which are capable of reproducing more than once will display an overlapping of generations, which basically means that parental cohorts and progeny cohorts can be alive and potentially competing with one another at the same time. Note that another way of saying this is that when life expectancies exceed the minimum time between generations, generations will overlap. Mortality. Death rate. Death rate is the rate at which individuals of a certain age die. Note that death rates often vary with age, with either the very young or the very old displaying the greatest death rates. Note additionally that population growth occurs when overall birth rates exceed overall death rates. Sex ratio. More often than not, the rate at which a population may grow is dependent on the sex ratio within the population. The fewer females, the slower the rate of population growth. This, of course, is because uteruses are limited and males often can inseminate more than one female. This generalization falls apart, however, when males are limited in their ability to inseminate more than one female, or when males contribute significantly to the raising of offspring. Survivorship curves. Observing age structure graphically can provide insights into a species or a population's ecology. Survivorship curves graph cohort size against relative age. The typical survivorship curve shows cohort size declining with age. There exist three general types of survivorship curves. Type 1, 2, and 3. Note in the following survivorship curves that the y-axis is logarithmic. Type 2 survivorship curves. The simplest type of decline is exponential, i.e., the death rate for every cohort is the same. These survivorship curves graph as a straight line on semi-logarithmic graph paper, i.e., as presented in a typical survivorship curve. The individuals in populations that display a type 2 curve are those that both do not age and are born as fully fit as adults, e.g., Hydra. Individuals are lost in these populations mostly to accidents and predation. Other examples include butterfly, birds, mice, rabbit, and most of holometabolous insects. Type 1 survivorship curves. Because individuals tend to die exponentially due to accidents or predation, it often is a good strategy to reproduce relatively early in a lifespan rather than relatively late. That way individuals achieve reproduction while they still have a reasonable likelihood of being alive. This is assuming, of course, that the goal is a Darwinian one, i.e., maximizing one's reproductive output. Note that how such a strategy works is complicated if individual fecundity increases with age. Very often for a given species there will be some age at which individuals are maximally fecund. Species that combine maximum fecundity with early ages typically do so at the expense of their ability to survive long periods, i.e., this is an example of the principle of allocation. A survivorship curve of such individuals may display a relatively shallow slope while individuals are younger, i.e., maximally robust and maximally reproductive, but then show an abrupt increase in death rate at ages that are coincident to declines in fecundity. Humans, of course, have a type 1 survivorship curve. It is displayed by most of higher organisms such as mammals and even by Drosophila. Type 3 survivorship curves. The other side of the survivorship coin is the degree of investment in individual progeny. Some organisms invest a great deal in each offspring, and those organisms are ideally at least rewarded with relatively high survivorship at early ages. Other organisms invest little in individual offspring and display very low early age survivorship, which they make up for by producing buckets of offspring. Organisms that produce large numbers of cheap progeny and which display minimal declines in fecundity with age, if they survive their youth, display type 3 survivorship curves. Examples include sea turtles, oysters, pelagic fishes, and trees. That is, type 3 survivorship species have a very large rate of mortality when young, but should they survive their youth, they put significant energy into continued survival since the longer they survive, the more progeny they will produce. Life history. The traits that affect an organism's schedule of reproduction and survival, from birth through reproduction to death, make up its life history. The study of life history characteristics is a detailed study of those ecological and evolutionary parameters that impact on survivorship curves. In many cases, there are trade-offs between survival and traits such as clutch size, number of offspring per reproductive episode, frequency of reproduction, and investment in parental care. The traits that affect an organism's schedule of reproduction and death make up its life history. Of course, a particular life history pattern, like most characteristics of an organism, is a result of natural selection operating over evolutionary time. In other words, the Darwinian goal is to maximize lifetime reproductive output, and this can be achieved by having babies more rapidly or living longer, or some combination of the two, as well as by varying many additional details having to do with survival and reproduction. Allocation of limited resources. Darwinian fitness is measured not by how many offspring are produced, but by how many survive to produce their own offspring. Heritable characteristics of life history that result in the most reproductively successful descendants will become more common within the population. If we were to construct a hypothetical life history that would yield the greatest lifetime reproductive output, we might imagine a population of individuals that begin reproducing at an early age, have large clutch sizes, and reproduce many times in a lifetime. However, natural selection cannot maximize all these variables simultaneously, because organisms have a finite energy budget that mandates trade-offs. For example, the production of many offspring with little chance of survival may result in fewer offspring that can compete vigorously for limited resources in an already dense population. The life history we observe in organisms represent a resolution of several conflicting demands. An important part of the study of life histories has been understanding the relationship between limited resources and competing functions, time, energy, and nutrients that are used for one thing cannot be used for something else. These issues can be phrased in terms of three basic questions. How often should an organism breed? When should it begin to reproduce? How many offspring should it produce during each reproductive episode? The way each population resolves these questions results in the integrated life history patterns we see in nature. All one quote starting with C, but broken up for clarity. Many life history issues involve balancing the profit of immediate investment in offspring against the cost of future prospects of survival and reproduction. These issues can be summarized by three basic decisions: when to begin reproducing, how often to breed, and how many offspring to produce during each reproductive episode. The various choices are integrated into the life history patterns we see in nature. Semel Big Bang organisms that produce one clutch of offspring progeny per lifetime are said to be semelparous, i.e., to display semel parity. The advantage of semel parity is that at the point of reproduction few if any resources need to be devoted to survival past reproduction. Heteroparity repeated reproduction organisms that produce more than one clutch of offspring progeny per lifetime are said to be idroparous, i.e., to display heteroparity. The advantage of heteroparity is that it allows organisms to display more than one statistical shot at producing a successful litter. The critical factor in the evolutionary dilemma of Big Bang versus repeated reproduction is the survival rate of the offspring. If their chance of survival is poor or inconsistent, repeated reproduction will be favored. 5 age structure. In most populations, individuals are of different ages. The proportion of individuals in what group is called age structure of that population. For instance, in understory palm tree populations, Astrachaeum mexicanum, in evergreen forests of Mexico, had 50% individuals as seedlings, less than 2 years old, 19% as saplings, 8-year-old, 5% as 30-year-old adults, and so until 70-year-old trees made up less than 2% of the population. Age pyramids. Age distribution is important, as it influences both natality and mortality of the population. The ratio of the various age groups in a population determines the current reproductive status of the population, thus anticipating its future. From an ecological viewpoint, there are 3 major ecological ages, age groups in any population. These are paraproductive, reproductive, and post-reproductive. The relative duration of these age groups in proportion to the lifespan varies greatly with different organisms. In man, the 3 ages are relatively equal in length, about a third of his life falling in each class. Many plants and animals have a very long paraproductive period. Some animals, particularly insects, have extremely long paraproductive periods, a very short reproductive period, and no post-reproductive period. The model representing geometrically the proportions of different age groups in the population of any organism is called age pyramid. The 3 hypothetical pyramid types are shown in figure, which are a pyramid with broad base. It indicates a high percentage of young individuals. In rapidly growing young populations, birth rate is high and population growth may be exponential as in yeast, housefly, paramecium, etc. Under such conditions, each successive generation will be more numerous than the preceding one, and thus a pyramid with broad base would result figure A. A bell-shaped polygon. It indicates a moderate proportion of young to old. As the rate of growth becomes slow and stable, i.e. the pre-reproductive and reproductive age group become more or less equal in size, post-reproductive group remaining as the smallest, there results a bell-shaped structure, figure B. An urn-shaped figure. It indicates a low percentage of young individuals. If the birth rate is drastically reduced, the paraproductive group dwindles in proportion to the other two groups, and it results in an urn-shape figure, figure C, which indicates that population is dying off. Wild density reveals little about difference between populations in developed and developing countries. Age structure highlights some of the cause of rapid population growth in the latter. Developing countries have a much greater preponderance of young people, and the side of pyramids become concave. Such a shape means high population growth, not only at present but also likely in future. Life tables. Information on natality and mortality in different ages and sexes can be combined in the form of life tables. From these, it is possible to estimate the growth or decline of a population. As with survivorship curves, life tables are standardized to follow the progress of a cohort. In each table, there are columns for age of individuals, number surviving to each age, the number dying in each age group, the proportion dying from the previous age category, fertility rate, and the number of young born by each age groups. The information obtained from these figures provides the net reproductive rate of the population, i.e., offspring left by each individual. Similarly, from life table, mortality in a logarithmic form is also obtained. These are then used to calculate the rate of population growth. 6. Population growth. The simplest case of population growth is that which occurs when there exist no limitations on growth with environment. In such situations, two things occur: the population displays its intrinsic rate of increase, the population experiences exponential growth. Biotic potential and intrinsic rate of growth. Each population has the inherent power to grow. When the environment is unlimited space, food, other organisms not exerting a limiting effect, the specific growth rate, i.e., the population growth rate per individual, becomes constant and maximum for the existing conditions. The value of the growth rate under these favorable conditions is maximal, is characteristic of a particular population age structure, and is a single index of the inherent power of a population to grow. It may be designated by the symbol R, which is the exponent in the differential equation for population growth in an unlimited environment under specific physical conditions. R represents intrinsic rate of population increase. The index R is actually the difference between the instantaneous specific natality rate, i.e., rate per time per individual, and the instantaneous specific death rate, and may thus be expressed. R equals BD. The overall population growth rate under unlimited environmental conditions R depends on the age composition and the specific growth rates due to reproduction of component age groups. Thus, there may be several values of R for a species depending upon population structure. When a stationary and stable age distribution exists, the specific growth rate is called the intrinsic rate of natural increase, or Rmax. The maximum value of R is often called by the less specific but widely used expression biotic potential or reproductive potential. Thus, with this term, one is able to put together natality, mortality, and age distribution. The ranges of the intrinsic rate of natural increase for various kinds of organisms are shown in Table 7.1. Chapman 1928 proposed the term biotic potential to designate maximum reproductive power. He defined it as the inherent property of an organism to reproduce, to survive, i.e., to increase in numbers. It is sort of the algebraic sum of the number of young produced at each reproduction, the number of reproduction in a given period of time, the sex ratio, and their general ability to survive under given physical conditions. For details, reader may refer to Graham 1952. But under natural conditions, this is a rare phenomenon, since environmental conditions do not permit unlimited growth of any population. Its size is kept under natural check. The difference between the maximum R biotic potential and the rate of increase which occurs in an actual laboratory or field condition is often taken as a measure of the environmental resistance, which is the sum total of environmental limiting factors which prevent the biotic potential from being realized. Organisms approximately biotic potential. R per year: large mammals 0.02, 0.5 birds 0.05, 1.5 small mammals 0.38 larger invertebrates 1030 insects 450 small invertebrates 30,800 including large protozoans. Protozoa and unicellular algae 600 2000 bacteria 3020 00. Population dynamics. After having studied the various characteristics of a population, we attempt to follow the change in its population have characteristic patterns of increase which are called population growth forms. Such growth forms represent the interaction of biotic potential and environmental resistance. What are the theoretical bases that attempt to account for such changes? Approaches to study of population dynamics are I mathematical models, E laboratory studies, and E field studies. Mathematical models are of two types: theoretical models and simulation models. The former derive equations that may describe population changes, and the behavior of such models can be tested by comparing these with real populations. The latter simulation models use detailed data from real populations and try to predict future behavior of these populations under specific environmental conditions. Models are of use only if they explain facets of population dynamics of real populations. Their predictions are often tested experimentally using laboratory populations. Mathematical and laboratory studies are of value only if they help to explain the behavior of natural populations. Field studies are made, though these are complex. Theory of population growth. Exponential growth. Exponential growth simply means that a population size at a given time is equal to the population size at an earlier time, times some greater than one number. For example, if a population increased in size per unit time in the following manner: 1, 2, 4, 8, 16, 32, 64, 128, etc., or e.g., 1, 3, 9, 27, or 1, 5, 25, 125, etc., then the population is displaying exponential growth. Each unit time the population is increasing by a factor of 2 or 3 or 5 in the other examples. Note that exponential growth is occurring so long as the rate of increase per unit time is greater than a factor of 1, e.g., 2 or 4 or 10 or 1.2, etc. When population size is graphed against time, e.g., generations, a population growing exponentially displays a J-shaped curve. Note differences in intrinsic rates of growth. In this J-shaped curves, that result in differences in rates of exponential growth, declining intrinsic growth rates are seen going from left to right in this graph. There may be assumed a model of geometric increase that assumes that there is no environmental constraint on population growth. A geometrical series is one with a constant multiplier. The simplest example is binary fission in protozoa, where each individual gives 2 each time it reproduces. Starting with one individual, generation 0, there will be 2, 4, 8, 16, 32, 64. In succeeding generations, fission is synchronous. Term number n1 present in any generation t. The following equation is used. Nt equals no. 2t no is no. Present in generation 0. Thus the number in generation 3 will be n degree 3 equals 1, 2, 3 equals 8. This equation is for a population that doubles in each generation. A more generation equation would be nt equals no ert. This is the exponential growth equation, where e r is substituted for 2. E is a universal constant. The base of natural logarithms and has a value of 2.718. R is a constant for a particular population under specific environmental conditions and is called the intrinsic rate of natural increase. The significance of logarithms in exponential growth is shown in figure, which compares the predictions of the binary fission equation on arithmetic and logarithmic scales. The logarithmic plot is a straight line, meaning that the number added in any time period is proportional to the number present at the beginning of the period. Compare with survivorship curve diagonal in figure 6, which is an exponential decline. The intrinsic rate of natural increase R is easy to calculate if natality and mortality rates are known. For example, for each of the 14 million people present in a country in 1980, 0.028 were born and 0.008 till during the year. R equals natality rate minus mortality rate, or 0.028, 0.008 per year. Substituting in the exponential growth equation, the number present in 1990 is predicted as nt equals no ert. N10 equals 14 million by 2.718, 0.02 x 10 equals 17 million. Note this is only strictly correct if the population is growing exponentially with constant birth and death rates in each structure, and there is no integration or emigration. In a rich culture medium, bacteria grown under aerobic conditions achieve a final concentration of 2 to 5 x 10 9 cells per milliliter in about 12 to 18 hours. Although plotted on a different time scale, the human growth curve looks the same. The human population at similar points on the growth curve are shown. When population size is graphed against time, e.g., generations, a population growing exponentially displays a straight line curve when graphed on some logarithmic graph paper. For example, below is a graph of the exponential increase in the computer processing power available per dollar. Note that on log linear graph paper, this curve is approximately a straight line. The J-shaped curve of exponential growth is characteristic of populations that are introduced into a new or unfilled environment, or whose numbers have been drastically reduced by catastrophic event and rebounding. In other words, a population that is in an environment lacking limits will grow exponentially. Indeed, a population that is capable of growing will tend to grow exponentially, and the rate at which growth will occur will be a function of Rmax and the degree to which the environment matches the ideal environment in which an organism is capable of achieving Rmax. Does it occur in nature? Most populations do not show exponential increase because their environment prevents this. In an ecosystem, other species present, a variety of abiotic conditions, etc., act in a way that a given population will have an upper size limit that cannot be exceeded. Such a limit is called carrying capacity of the environment for that population. Carrying capacity is determined by the availability of resources, food, and space. Limits on population growth. Exponential growth cannot go on forever. Sooner or later, any population will run into limits in their environment. Carrying capacity K. Populations subsist on a finite amount of available resources, and as the population becomes more crowded, each individual has access to an increasingly smaller share. Ultimately, there is a limit to the number of individuals that can occupy a habitat. Ecologists define carrying capacity as the maximum stable population size that a particular environment can support over a relatively long period of time. Carrying capacity, symbolized as K, is a property of the environment, and it varies over space and time with the abundance of limiting resources. In other words, for any given organism, there will be a maximum number of individuals that the environment can support without the environment being consequently degraded to the point where it can no longer support that number of individuals. Generally, as population size approaches carrying capacity, the amount of some key resource declines per capita to the point where individuals experience either a higher death rate or a lower fecundity. Thus, as population size approaches carrying capacity, the rate of population growth declines towards zero. Logistic growth. Logistic growth is a mathematical description of population growth that employs two parameters, Rmax and K, and two variables, n and t. The logistic growth curve is S-shaped. That is, the population grows exponentially at a rate which is determined by Rmax and the suitability of a given environment to an organism's needs until population size is sufficient that the limitations associated with the carrying capacity of the environment are approached. This slows the rate of population growth in a way such that the larger the population becomes, the slower its rate of growth. This slowing of the growth transforms the curve from a J-shaped one to an S-shaped one. Ultimately, the rate of growth of the population reaches zero at the carrying capacity. Because the rate at which a population grows changes with the density of organisms that are currently in the population, the logistic model is said to be density dependent. That is, population growth grows as population density approaches that dictated by an environment's carrying capacity for that population. Note that populations do not typically display the idealized logistic growth seen with the model. One deviation from idealized logistic growth is delayed feedback. This can cause population size overshooting. In fact, what is typically observed in real populations is not just effects of random events, but also population sizes which vary up and down around the carrying capacity rather than remaining invariant exactly. The carrying capacity logistic equation was devised by Verhulst in 1838 to describe population growth with an upper limit. Suppose environment has a carrying capacity K for a particular population. Then the logistic equation assumes that the intrinsic rate of natural increase R is progressively reduced as population size increases toward the carrying capacity. If there are 10 individuals already present, n equals 10 and K equals 100 individuals, the remaining resources can support a further K n equals 90 individuals, and the proportion of remaining resources is K and K equals 0.9. The logistic equation simply assumes that R is reduced in relation to proportion of remaining resources. The equation is derived from the exponential such that T RTK KNNE minus equals 0. The logistic growth equation. Suppose R equals 1, then when n equals 10, the growth rate actually achieved, R K and K, is 1 by 0.9. When n equals 90, K and K equals 0.1 and the growth rate is 1 by 0.1 and so on, giving the progressive decline in realized growth rate. The logistic curve is S-shaped on arithmetic coordinates and is always less steep than its exponential equivalent, figure A. A comparison of the same curve on some logarithmic coordinates is given in figure 7b using differential calculus. The logistic equation becomes K. Kn Rn dt dn minus equals growth of laboratory and field populations. From the above account of carrying capacity, one would expect exponential growth only under circumstances of no environmental resistance. Such a growth is possible in laboratory culture if excess organisms are removed to avoid overcrowding. However, in nature, exponential increase in population experiences catastrophic decline for insect population. Under adequate food and climate, population increased, but then declined when these turned unfavorable. In the laboratory, logistic growth has been observed in bacteria, yeast, algae, and protozoa. This is shown for paramecium. In laboratory cultures, somewhat much less fit to logistic is usually found in metazoans as beetle, like the zooty bean weevil Calosobruchus chinesis, but populations do often fluctuate around the carrying capacity. There are several reasons: competition, loss in female fecundity, increased egg mortality, etc. High density of this beetle. In the field, direct observation of variation and limitation are rare. However, there is a logistic model of wildebeest Conocchides serenus in Tanzania and Kenya. The population levels of K determined by food availability following its low density. Modifications of logistic theory. Following assumptions are implicit in the logistic equation. I environment is constant such that R and K do not charge. E there are no time lags in response to the population to change in its density. E individuals have identical ecological characteristics in terms of their responses to density, regardless of age or sex. I.e. growth is continuous and B age structure does not change in successive generations. These assumptions are unlikely to be met in laboratory and will never obtain in the field. Therefore, logistic theory has been suitably modified to make it biologically reasonable. These are I inclusion of a time lag. E there are fluctuations in the carrying capacity. E there may be chance events for survival and reproduction of an individual as well as for their death. Due to landslide, etc. I.e. discontinuous growth of some populations which grow in discrete steps with little or no overlap between successive generations. Keeping in view the above, it is natural to ask, are then mathematical models of any use? The answer is yes, because L as theoretical abstractions, they set the crude limits to possible patterns of population growth. Observations on real populations can be assessed within these limits. 2. As models become more refined, they more closely fit the behavior of real populations. 1 can make increasingly accurate predictions of population behavior. 3 from above 1 and 2. It follows that population models can be applied to real practical problems of human population growth and the management of plant and animal populations. 7. Regulation of population density. The logistic model and its derivatives assume that a population will level off at its carrying capacity, that there is an upper limit to population density set by the environment and that the population is regulated at around that level. The significance of regulation in population has been a subject of controversy among ecologists for last more than years. What regulates population? Krebs 1985 presented an account of this subject. Nature of factors that influence population density can only be increased by natality or immigration and decreased by mortality or immigration. These factors may be density dependent or density independent in their effects. Density dependent factors. Density dependent limits on population growth are ones that stem from interspecific competition. Typically, the organisms best suited to compete with another organism are those from the same species. Thus, the actions of conspecifics can very precisely serve to limit the environment, e.g., eat preferred food, obtain preferred shelter, etc. Actions of that serve to limit the environment for conspecifics, e.g., eating, excreting wastes, using up non-food resources, taking up space, defending territories, are those that determine carrying capacity. They are referred to as density dependent because the greater the density of the population, the greater their effects. Density dependent factors may exert their effect by reducing birth rates, increasing death rates, extending generation times, or by forcing the migration of conspecifics to new regions. The impact of disease on a population can be density dependent if the transmission rate of the disease depends on a certain level of crowding in the population. A death rate that rises as population density rises is said to be density dependent, as is a birth rate that falls with rising density. Density dependent rates are an example of negative feedback. In contrast, a birth rate or death rate that does not change with population density is said to be density independent. Negative feedback prevents unlimited population growth. Predation can also be density dependent since predators often can switch prey preferences to match whatever prey organisms are most plentiful in a given environment. Many predators, for example, exhibit switching behavior. They begin to concentrate on a particularly common species of prey when it becomes energetically efficient to do so. Density independent factors. Density independent effects on population sizes or structures occur to the same extent regardless of population size. These can be things like sudden changes in the weather. Over the long term, many populations remain fairly stable in size and are presumably close to a carrying capacity that is determined by density dependent factors. Superimposed on this general stability, however, are short-term fluctuations due to density independent factors. C2. Life history adaptive strategies of development R and K selection. Logistic law. It can be said that, overall, natural selection, which enables the colonization of ecosystems, has put into place 2 major types of species. See table. Even though there are several models for growth of individuals in a population, the most commonly recognized is that of logistic law of development of populations big. K. KNRN. DT. Dn minus equals. Where n equals number of individuals or biomass at an instant t. R equals coefficient intrinsic rate of growth, and K equals maximum number of individuals the biotope can hold as a function of its resources. The curve always has the same shape, but the greater the value of coefficient R, the more abruptly the curve rises. On the other hand, when n approaches K, the value n, K is close to 0, the product RNO equals 0, the growth is thus null, the environment is saturated, and its potential does not allow it to advantageously support any more individuals. Table. Comparative table of R strategist and K strategist. R strategist, K strategist, small size. High productivity. Sexual precocity. High mortality. Short lifespan. Considerable. Waste of energy. Generalist. Species. Population. Density independent of. Environmental variations. Demographic. Regulation not linked to. Population density. Pioneering and. Colonizing species. Highly. Large size. Low productivity. Long period of sexual immaturity. Low mortality, long lifespan. Economical use of energy. Specialist. Species. Population density closely dependent on environmental variations. Demographic. Regulation linked to population density. Species closely associated with climax low fluctuation in numbers. Fluctuating numbers. 1. The R strategists. The R strategists are species with a very high coefficient of growth. They are thus located near the base of the curve. Among plants, the grasses are members of family Poaceae are typical R strategists. They are annual plants that spend 70% of their energy on seed production. With their phenomenal capacity for dissemination and their low needs, they have a particular aptitude for colonizing spaces that are devoid of all other vegetation. Among animals, a small sparrow, the crossbill, is also representative of this group. It feeds on conifer seeds and in the spring produces 2 broods of 6 to 8 young each, which are capable of reproducing in the same autumn. The crossbill lives only 2 years on average, but each pair can in good conditions have about 40 offspring. Characteristics. Size of individuals. The R strategists are small, and there seems to be an explanation for their size. For example, a spherical, unicellular alga has a volume, cubic function corresponding to the classic formula V equals 4/3 pi r3. The zone of exchange with a medium, for photosynthesis, respiration, or absorption, is the cell membrane, the surface of which is a square function, since it follows the formula S equals pi r2. When the size of the organism increases, the shape being constant, the SN ratio diminishes. Its surface of exchanges grows proportionately less rapidly than its volume. Its metabolic activity is affected to the extent that it absorbs nutrients less quickly. Transfers of gases and nutrients are not as efficient as required by the increase in volume. The R strategists, which have an active metabolism, thus develop well when they remain small. Productivity. Productivity is very high. The species that follow the R strategy, not requiring much energy, establish themselves right away and grow rapidly. Such is the case with weeds that invade any abandoned field. Prolificity. The R strategists have a high prolificity because of their high sexual precocity and the large number of seeds or descendants they produce. This high prolificity is accompanied by enormous expenditure of energy, much of it purely loss, which leads to considerable waste. Lifespan. Mortality is very high, and the enormous expenditures devoted to reproduction that characterize R strategists are accompanied by a short lifespan. There are many descendants, but only some survive and become adults capable of reproduction. Mode of life. The R strategists can only satisfy their energy needs by having a wide range of feed. In abiotic as well as biotic terms, they have a generalist mode of life. Population density. Because of their wide tolerance, these ubiquitous species are independent of environmental fluctuations, which affect them only slightly. Similarly, since they act as pioneer species that often colonize new or virgin environments, their demographic regulation is not dependent on the density of their population. Also, their numbers fluctuate greatly, as appropriate for colonizing species. Since nature always optimizes the flows of matter and energy, these wasteful species are quite soon replaced by others that are more economical and efficient and that have K strategies. 2. The K strategists. Unlike the R strategists, the K strategists are species that are highly demanding but well adapted and profiting fully from the potential of their environments. Under the logistic law, environments favor K over R. The K strategists are at the top of the curve that characterizes equilibrium between the population and the possibilities of the biotope. In plants, the type example is the oak, which lives for several centuries but fructifies quite slowly. This tree spends only 7% of its energy in producing acorns. Among animals, the large albatross of the Australian seas attains puberty only at the age of 10. The female lays a single egg every 2 years, but as the individuals live an average of 80 years, this gives the potential of 40 descendants, the same number as for the crossbill. Characteristics. Size of individuals. The K strategists are always large. All the same, at the same trophic level, a large bacterium behaving as a K strategist will always be smaller than a tiny R strategist mammal. Productivity. Since they are very precisely adapted to their environmental conditions, the K strategists by themselves have a low productivity. But since, like other species, they exploit other trophic sectors, the biotope as a whole is used and the total productivity is optimal. Prolificity. The K strategists have a low prolificity. They have in fact a long period of sexual immaturity and the size of litters or broods is limited. Lifespan. Their mortality is very low. The animals raise only a few young, but they give them much attention. They teach the young to feed, hunt, and defend themselves, so well that almost all become adults. The lifespan is therefore long. Mode of life. The cave strategists, unlike the R strategists, are economical with energy. They feed on only a small part of the food chain but waste little. One can call them specialist species that are highly adapted to the nutritional and ambient abiotic conditions. Population density. The number of descendants is highly dependent on the potential of the environment. Population density will therefore vary considerably according to the biotope. The demographic regulation is thus here totally linked to the demography. If the environmental conditions remain stable, fluctuations in numbers will remain limited. 3. Why do the less competitive R strategists not disappear? All ecosystems are not stable. A single cataclysm can disturb the cave strategists, which, like all specialists, are effective only when the environment is stable. The least disturbed catastrophe for them. They are thus very fragile and sensitive to the vagaries of nature. And nature never ceases to produce climatic accidents, flood, drought, frost, or geological accidents, earthquakes, landslides, erosion, to cite only the major disturbances. Just as an economic disaster rapidly creates an army of unemployed, an ecological disturbance leads to the disappearance of cave strategists. Their place does not long remain unoccupied. Their place does not long remain unoccupied, since R strategists, which are tolerant of various living conditions, adapt themselves to these disturbances and populate the ecosystem until it becomes stable and perhaps newly occupied by efficient cave strategists. When lightning strikes an old tree in a primeval forest, it creates a clearing that provides favorable conditions for the growth of raspberry bushes. These bushes were stunted in the shade of the large tree and regain vitality when the tree is gone. The R strategists thus prove to be valuable in case of disruptions. They are pioneering and colonizing species, but they never attain the cave threshold because they find themselves competing with the more competitive cave strategists when the environment stabilizes. There is in fact a gradient of evolution with intermediate strategies. Note: the human species is not free of this law. In the northern or rich countries, the environment is nearly stable for the large majority of the population. Food is abundant and nutritious, health is monitored, conditions of life convenient with heated houses, for example. The lifespan is increasingly long and the average family has 2 children who are well educated and well cared for. These criteria correspond to those that have been defined for cave strategists. It is very different in developing countries, where the environment is unstable. Drought, poverty, and political, religious, or ethnic conflicts keep it in an unstable condition. This leads the human species to adopt our strategies. The population is high. Births are numerous, but infant mortality is excessive as a result of famine, disease, and parasites associated with lack of health care, poor living conditions, and a lack of potable water. C3. Concept of metapopulations. A metapopulation consists of a group of spatially separated populations of the same species which interact at some level. The term metapopulation was coined by Richard Levins in 1969 to describe a model of population dynamics of insect pests in agricultural fields, but the idea has been most broadly applied to species in naturally or artificially fragmented habitats. In Levins' own words, it consists of a population of populations. A metapopulation is generally considered to consist of several distinct populations together with areas of suitable habitat which are currently unoccupied. In classical metapopulation theory, each population cycles in relative independence of the other populations and eventually goes extinct as a consequence of demographic specificity, fluctuations in population size due to random demographic events. The smaller the population, the more prone it is to extinction. Although individual populations have finite lifespans, the metapopulation as a whole is often stable because immigrants from one population, which may, for example, be experiencing a population boom, are likely to recolonize habitat which has been left open by the extinction of another population. They may also emigrate to a small population and rescue the population from extinction, called the rescue effect. The development of metapopulation theory, in conjunction with the development of source sink dynamics, emphasize the importance of connectivity between seemingly isolated populations. Although no single population may be able to guarantee the long-term survival of a given species, the combined effect of many populations may be able to do this. Metapopulation theory was first developed for terrestrial ecosystems and subsequently applied to the marine realm. Kritzer and Sale 2006. In fishery science, the term subpopulation is equivalent to the metapopulation science term local population. Most marine examples are provided by relatively sedentary species occupying discrete patches of habitat, with both local recruitment and recruitment from other local populations in the larger metapopulation. Kritzer and Sale have argued against strict application of the metapopulation definitional criteria that extinction risks to local populations must be non-negligible. The most important contributor to metapopulation theory is the Finnish biologist Ilkka Hansky of the University of Helsinki. Predation and oscillations. The first experiments with predation and spatial heterogeneity were conducted by G.F. Gause in the 1930s, based on the Lacoville-Terra equation, which was formulated in the mid-1920s, but no further application had been conducted. The Lacoville-Terra equation suggested that the relationship between predators and their prey would result in population oscillations over time based on the initial densities of predator and prey. Gause's early experiments to prove the predicted oscillations of this theory failed because the predator-prey interactions were not influenced by emission. However, once immigration was introduced, the population cycles accurately depicted the oscillations predicted by the Lacoville-Terra equation, with the peaks in prey abundance shifted slightly to the left of the peaks of the predator densities. Huppeker's experiments expanded on those of Gause by examining how both the factors of migration and spatial heterogeneity lead to predator-prey oscillations. Huppeker's experiments on predator-prey interactions, 1958. In order to study predation and population oscillations, Huppeker used mite species, one being the predator and the other being the prey. He set up a controlled experiment using oranges, which the prey fed on, as a spatially structured habitat in which the predator and prey would interact. At first, Huppeker experienced difficulties similar to those of Gause in creating a stable predator-prey interaction. By using oranges only, the prey species quickly went extinct, followed consequently with predator extinction. However, he discovered that by modifying the spatial structure of the habitat, he could manipulate the population dynamics and allow the overall survival rate for both species to increase. He did this by altering the distance between the prey and oranges, their food, establishing barriers to predator movement, and creating corridors for the prey to disperse. These changes resulted in increased habitat patches and in turn provided more areas for the prey to seek temporary protection. When the prey would go extinct locally at one habitat patch, they were able to reestablish by migrating to new patches before being attacked by predators. This habitat spatial structure of patches allowed for coexistence between the predator and prey species and promoted a stable population oscillation model. Although the term metapopulation had not yet been coined, the environmental factors of spatial heterogeneity and habitat patchiness would later describe the conditions of a metapopulation relating to how groups of spatially separated populations of species interact with one another. Huppeker's experiment is significant because it showed how metapopulations can directly affect the predator-prey interactions and in turn influence population dynamics. Aggregation effect and stability of predator-prey interactions. The stability of predator-prey interactions in patchy environments is reinforced when an aggregation effect occurs. Aggregation effect is when predators are more greatly attracted to habitat patches with high prey densities. Therefore, areas with low prey densities are relieved from the pressure of predation and are able to generate a larger population and avoid extinction. The Levins model. Levins' original model applied to a metapopulation distributed over many patches of suitable habitat with significantly less interaction between patches than within a patch. Population dynamics within a patch were simplified to the point where only presence and absence were considered. Each patch in his model is either populated or not. Let n be the fraction of patches occupied at a given time. During a time step, each occupied patch can become unoccupied with an extinction probability E. Additionally, 1 minus n of the patches are unoccupied. Each of these may become populated by colonization. Let's see the constant rate of propagule generation for each of the unoccupied patches. This yields a probability of Cn for each unoccupied patch to be colonized. So for each time step, the change in the proportion of occupied patches, dn dt, is. This takes on a sigmoid shape similar to the logistic model. The equilibrium value of n can be calculated by setting dn to be equal to 0. Solving for n gives either n equals 0 or. This result, that n is always less than 1, implies that some fraction of a species habitat will always be unoccupied. Stochastic patch occupancy models, SPOMs. One major drawback of the Levins model is that it is deterministic, whereas the fundamental metapopulation processes are stochastic. Metapopulations are particularly useful when discussing species in disturbed habitats, and the viability of their populations, i.e., how likely they are to become extinct in a given time interval. The Levins model cannot address this issue. For conservation biology purposes, metapopulation models must include a, the finite nature of metapopulations, how many patches are suitable for habitat, and b, the probabilistic nature of extinction and colonization. Also, note that in order to apply these models, the extinctions and colonizations of the patches must be asynchronous. Stochasticity in metapopulations. Huffaker's studies of spatial structure and species interactions are an example of early experimentation in metapopulation dynamics. Since the experiments of Huffaker and Levins, models have been created which integrate stochastic factors. These models have proven that the combination of environmental variability, stochasticity, and relatively small migration rates cause indefinite or unpredictable persistence. However, Huffaker's experiment almost guaranteed infinite persistence because of the controlled immigration variable. These species interactions. Types of interactions: interspecific competition, herbivora, carnivory, pollination, symbiosis. Biological interactions result from the fact that organisms in an ecosystem interact with each other. In the natural world, no organism is an autonomous entity isolated from its surroundings. It is part of its environment, rich in living and non-living elements, all of which interact with each other in some fashion. An organism's interactions with its environment are fundamental to the survival of that organism and the functioning of the ecosystem as a whole. Sign-mediated interactions in which molecules serve as signs of the characteristic feature of communicative interactions. In ecology, biological interactions are the relationships between two species in an ecosystem. These relationships can be categorized into many different classes of interactions based either on the effects or on the mechanism of the interaction. The interactions between two species vary greatly in these aspects as well as in duration and strength. Species may meet once in a generation, e.g. pollination, or live completely within another, e.g. endosymbiosis. Effects may range from one species eating the other, predation, to mutual benefit, mutualism. The interactions between two species need not be through direct contact. Due to the connected nature of ecosystems, species may affect each other through intermediaries such as shared resources or common enemies. Interactions categorized by effect. Effect type of interaction. 0 neutralism, 0 commensalism plus 0 commensalism, competition plus mutualism. Plus predation or parasitism. Some types of relationships listed by the effect they have on each partner. 0 feet is no effect, is detrimental, and plus is beneficial. Terms which explicitly indicate the quality of benefit or harm in terms of fitness experienced by participants in an interaction are listed below. There are 6 possible combinations, ranging from mutually beneficial through neutral to mutually harmful interactions. The level of benefit or harm is continuous and not discrete, such that an interaction may be trivially harmful through to deadly, for example. It is important to note that these interactions are not always static. In many cases, two species will interact differently under different conditions. This is particularly true in, but not limited to, cases where species have multiple, drastically different life stages. Neutralism. Neutralism describes the relationship between two species which do interact but do not affect each other. It is to describe interactions where the fitness of one species has absolutely no effect whatsoever on that of other. True neutralism is extremely unlikely and impossible to prove. When dealing with the complex networks of interactions presented by ecosystems, one cannot assert positively that there is absolutely no competition between or benefit to either species. Since true neutralism is rare and non-existent, its usage is often extended to situations where interactions are merely insignificant or negligible. Amensalism. Amensalism between two species involves one impeding or restricting the success of the other without being affected positively or negatively by the presence of the other. It is a type of symbiosis. Usually this occurs when one organism exudes a chemical compound as part of its normal metabolism that is detrimental to another organism. The bread mold penicillium is a common example of this. Penicillium secrete penicillin, a chemical that kills bacteria. A second example is the black walnut tree, Juglans nigra, which secrete juglone, a chemical that harms or kills some species of neighboring plants from its roots. This interaction may still increase the fitness of the non-harmed organism though, by removing competition and allowing it access to greater scarce resources. In this sense, the impeding organism can be said to be negatively affected by the other's very existence, making it a plus interaction. Antibiosis or allelopathy also explain similar interactions. Competition. Competition is an interaction between individuals or populations that is mutually detrimental. Symbiosis is a particular case in which the interaction is so mutually detrimental that it results in death, as in the case of some parasitic relationships. It is a rare and necessarily short-lived condition as evolution selects against it. The term is seldom used. Antagonism. In antagonistic interactions, one species benefits at the expense of another. Predation is an interaction between organisms in which one organism captures class from another. It is often used as a synonym for carnivory, but in its widest definition includes all forms of one organism eating another, regardless of trophic level, e.g. herbivora, closeness of association, e.g. parasitism, and parasitism, and harm done to prey, e.g. grazing. Other interactions that cannot be classed as predation, however, are still possible, such as petition mimicry, where an organism bears a superficial similarity of at least one sort, such as a harmless plant coming to mimic a poisonous one. Ecological facilitation. The following two interactions can be classed as facilitative. Facilitation describes species interactions that benefit at least one of the participants and cause no harm to either. Facilitations can be categorized as mutualisms, in which both species benefit, or commensalisms, in which one species benefits and the other is unaffected. Much of classic ecological theory, e.g., natural selection, niche separation, metapopulation dynamics, has focused on negative interactions such as predation and competition, but positive interactions facilitation or receiving increasing focus in ecological research. Commensalism. Commensalism benefits one organism and the other organism is neither benefited nor harmed. It occurs when one organism takes benefits by interacting with another organism by which the host organism is not affected. A good example is remora living with a shark. Remora eat leftover food from the shark. The shark is not affected in the process as remora eat only leftover food of the shark which doesn't deplete the shark's resources. Mutualism. Mutualism is an interaction between two or more species, where species derive a mutual benefit, for example an increased carrying capacity. Similar interactions within a species are cooperation. Mutualism may be classified in terms of the closeness of association, the closest being symbiosis, which is often confused with mutualism. One or both species involved in the interaction may be obligate, meaning they cannot survive in the short or long term without the other species. Though mutualism has historically received less attention than other interactions such as predation, it is a very important subject in ecology. Examples include cleaner fish, pollination and seed dispersal, gut flora and nitrogen fixation by fungi. Interactions classified by mechanism. Symbiosis. The term symbiosis Greek, living together, can be used to describe various degrees of close relationship between organisms of different species. Sometimes it is used only for cases where both organisms benefit. Sometimes it is used more generally to describe all varieties of relatively tight relationships, i.e. even parasitism, but not predation. Some even go so far as to use it to describe predation. It can be used to describe relationships where one organism lives on or in another, or it can be used to describe cases where organisms are related by mutual stereotypic behaviors. In either case, symbiosis is much more common in the living world and much more important than is generally assumed. Almost every organism has many internal parasites. A large percentage of herbivores have mutualistic gut fauna that help them digest plant matter, which is more difficult to digest than animal prey. Coral reefs are the result of mutualisms between coral organisms and various types of algae that live inside them. Most land plants and thus, one might say, the very existence of land ecosystems rely on mutualisms between the plants which fix carbon from the air, and mycorrhizal fungi which help in extracting minerals from the ground. In fact, the evolution of all eukaryotes plants, animals, fungi, protists is believed to have resulted from symbiosis between various sorts of bacteria, endosymbiotic theory. Competition. Competition can be defined as an interaction between organisms or species, in which the fitness of one is lowered by the presence of another. Limited supply of at least one resource, such as food, water, and territory used by both is required. 12. Competition is one of many interacting biotic and abiotic factors that affect community structure. Competition among members of the same species is known as interspecific competition, while competition between individuals of different species is known as interspecific competition. Competition is not always a straightforward, direct interaction either, and can occur in both a direct and indirect fashion. According to the competitive exclusion principle, species less suited to compete for resources should either adapt or die out. According to evolutionary theory, this competition within and between species for resources plays a critical role in natural selection. D2. Competition. Organisms grow, reproduce, and die. They are affected by the conditions in which they live and by the resources that they obtain. But no organism lives in isolation. Each, for at least part of its life, is a member of a population composed of individuals of its own species. Individuals of the same species have very similar requirements for survival, growth, and reproduction, but their combined demand for a resource may exceed the immediate supply. The individuals then compete for the resource and, not surprisingly, at least some become deprived. This topic is concerned with the nature of such interspecific competition, its effects on the competing individuals and on populations of competing individuals. We begin with a working definition. Competition is an interaction between individuals, brought about by a shared requirement for a resource, and leading to a reduction in the survivorship, growth, and/or reproduction of at least some of the competing individuals concerned. We can now look more closely at competition. Competition can be defined as an interaction between organisms or species, in which the fitness of one is lowered by the presence of another. Limited supply of at least one resource, such as food, water, and territory used by both is required. Competition both within and between species is an important topic in ecology, especially in community ecology. Competition is one of many interacting biotic and abiotic factors that affect community structure. Competition among members of the same species is known as interspecific competition, while competition between individuals of different species is known as interspecific competition. Competition is not always a straightforward, direct interaction either, and can occur in both a direct and indirect fashion. Consider, initially, a simple hypothetical community, a thriving population of grasshoppers, all of one species feeding on a field of grass also of one species. To provide themselves with energy and material for growth and reproduction, grasshoppers eat grass, but in order to find and consume that grass they must use energy. Any grasshopper might find itself at a spot where there is no grass because some other grasshopper has eaten it. The grasshopper must then move on and expend more energy before it takes in food. The more grasshoppers there are, the more often this will happen. An increased energy expenditure and a decreased rate of food intake may all decrease a grasshopper's chances of survival and also leave less energy available for development and reproduction. Survival and reproduction determine a grasshopper's contribution to the next generation. Hence, the more interspecific competitors for food a grasshopper has, the less its likely contribution will be. As far as the grass itself is concerned, an isolated seedling in fertile soil may have a very high chance of surviving to reproductive maturity. It will probably exhibit an extensive amount of modular growth and will probably therefore eventually produce a large number of seeds. However, a seedling that is closely surrounded by neighbors, shading it with their leaves and depleting the water and nutrients of its soil with their roots, will be very unlikely to survive, and if it does, will almost certainly form few modules and set few seeds. We can see immediately that the ultimate effect of competition on an individual is a decreased contribution to the next generation compared with what would have happened had there been no competitors. Interspecific competition typically leads to decreased rates of resource intake per individual, and thus to decreased rates of individual growth or development, or perhaps to decreases in the amounts of stored reserves or to increased risks of predation. These may lead, in turn, to decreases in survivorship and/or decreases in fecundity, which together determine an individual's reproductive output. Exploitation and interference. In many cases, competing individuals do not interact with one another directly. Instead, individuals respond to the level of a resource, which has been depressed by the presence and activity of other individuals. The grasshoppers were one example. Similarly, a competing grass plant is adversely affected by the presence of close neighbors, because the zone from which it extracts resources, light, water, nutrients has been overlapped by the resource depletion zones of these neighbors, making it more difficult to extract those resources. In such cases, competition may be described as exploitation, in that each individual is affected by the amount of resource that remains after that resource has been exploited by others. Exploitation can only occur, therefore, if the resource in question is in limited supply. In many other cases, competition takes the form of interference. Here individuals interact directly with each other, and one individual will actually prevent another from exploiting the resources within a portion of the habitat. For instance, this is seen amongst animals that defend territories and amongst the sessile animals and plants that live on rocky shores. The presence of a barnacle on a rock prevents any other barnacle from occupying the same position, even though the supply of food at that position may exceed the requirements of several barnacles. In such cases, space can be seen as a resource in limited supply. Another type of interference competition occurs when, for instance, two red deer stags fight for access to a harem of hinds. Either stag, alone, could readily mate with all the hinds, but they cannot both do so since matings are limited to the owner of the harem. Thus, interference competition may occur for a resource of real value, e.g. space on a rocky shore for a barnacle, in which case the interference is accompanied by a degree of exploitation, or for a surrogate resource, a territory, or ownership of a harem, which is only valuable because of the access it provides to a real resource, food, or females. With exploitation, the intensity of competition is closely linked to the level of resource present and the level required, but with interference, intensity may be high even when the level of the real resource is not limiting. Whether they compete through exploitation or interference, individuals within a species have many fundamental features in common, using similar resources and reacting in much the same way to conditions. Nonetheless, interspecific competition may be very one-sided. A strong, early seedling will shade a stunted, late one, an older and larger bryozoan on the shore will grow over a smaller and younger one. Hence, the ultimate effect of competition is far from being the same for every individual. Weak competitors may make only a small contribution to the next generation, or no contribution at all. Strong competitors may have their contribution only negligibly affected. Finally, note that the likely effect of interspecific competition on any individual is greater the more competitors there are. The effects of interspecific competition are thus said to be density dependent. According to the competitive exclusion principle, species less suited to compete for resources should either adapt or die out. According to evolutionary theory, this competition within and between species for resources plays a critical role in natural selection. Types of competition. By mechanism, the following terms describe mechanisms by which competition occurs, which can generally be divided into direct and indirect. These mechanisms apply equally to interspecific and interspecific competition. Male-male competition in red deer during rut is an example of interference competition within a species. Interference competition occurs directly between individuals via aggression, etc. when the individuals interfere with foraging, survival, reproduction of others, or by directly preventing their physical establishment in a portion of the habitat. Exploitation competition occurs indirectly through a common limiting resource which acts as an intermediate. For example, the use of the resources depletes the amount available to others, or they compete for space. Apparent competition occurs indirectly between two species which are both preyed upon by the same predator. For example, species and species B are both preys for predator C. The increase of species A will cause a decrease of species B because the increase of this would increase the number of predator C's, which in turn will hunt more of species B. Intraspecific competition. Intraspecific competition occurs when members of the same species vie for the same resources in an ecosystem, e.g. food or nutrients, light or space. For example, two trees growing close together will compete for light above ground and water and nutrients in the soil. Therefore, getting less resources, they will usually perform less well than if they grew by themselves. Adaptations to such an environment include growing taller, especially in forests, or developing a larger root system. Interspecific competition. Interspecific competition may occur when individuals of two separate species share a limiting resource in the same area. If the resource cannot support both populations, then lower fecundity, growth, or survival may result in at least one species. Interspecific competition has the potential to alter populations, communities, and the evolution of interacting species. An example among animals could be the case of cheetahs and lions, since both species feed on similar prey. They are negatively impacted by the presence of the other because they will have less food. In fact, lions sometimes steal prey items killed by cheetahs. Evolutionary strategies. In evolutionary contexts, competition is related to the concept of RK selection theory, which relates to the selection of traits which promote success in particular environments. The theory originates from work on island biogeography by the ecologists Robert McCarter and E.O. Wilson. In RK selection theory, selective pressures are hypothesized to drive evolution in one of two stereotype directions: weight selection. These terms, R and K, are derived from standard ecological algebra, as illustrated in the simple Bernoulli equation of population dynamics, where R is the growth rate of the population N and K is the carrying capacity of its local environmental setting. Typically, R-selected species exploit empty niches and produce many offspring, each of whom has a relatively low probability of surviving to adulthood. In contrast, K-selected species are strong competitors in crowded niches and invest more heavily in much fewer offspring, each of whom has a relatively high probability of surviving to adulthood. D3. Predation. In ecology, predation describes a biological interaction where a predator organism feeds on another living organism or organisms known as prey. Predators may or may not kill their prey prior to feeding on them, but the act of predation always results in the ecologically significant death of the prey. The other main category of consumption is detritivore, the consumption of dead organic material, detritus. It can at times be difficult to separate the two feeding behaviors. For example, where parasitic species prey on a host organism and then lay their eggs on it for their offspring to feed on its decaying corpse. The key characteristic of predation, however, is the predator's direct impact on the prey population. On the other hand, detritivores simply eat what is available and have no direct impact on the donor organisms. Classification of predators. The unifying theme in all classifications of predation is a predator lore in the fitness of its prey, or put another way, it reduces its prey's chances of survival, reproduction, or both. Ways of classifying predation surveyed here include grouping by trophic level or diet, by specialization, and by the nature of their interaction with prey. Functional classification. Classification of predators by the extent to which they feed on and interact with their prey is one way ecologists may wish to categorize the different types of predation. Instead of focusing on what they eat, this system classifies predators by the way in which they eat, and the general nature of the interaction between predator and prey species. Two factors are considered here: how close the predator and prey are physically. In the latter two cases, the term prey may be replaced with host. Additionally, whether or not the prey directly killed by the predator is considered, with the first and last cases involving certain death. True predation. A true predator is one which kills and eats another organism. Whereas other types of predator all harm their prey in some way, this form results in their instant death. Predators may hunt actively for prey, or sit and wait for prey to approach within striking distance, as in ambush predators. Some predators kill large prey and dismember or chew it prior to eating it, such as a jaguar, while others may eat their usually much smaller prey whole, as does a bottlenose dolphin or any snake, or a duck or stork swallowing a frog. In some cases, the prey organism may die in the mouth or digestive system of the predator. Baleen whales, for example, eat millions of microscopic plankton at once, the prey being broken down well after entering the whale. Sea predation is another form of true predation, as seeds represent potential organisms. Predators of this classification need not eat prey entirely. For example, some predators cannot digest bones, while others can. Some may merely eat only part of an organism, as in grazing, but still consistently cause its direct death. Grazing. Grazing organisms may also kill their prey species, but this is seldom the case. While some herbivores like zooplankton live on unicellular phytoplankton and have no choice but to kill their prey, many only eat a small part of the plant. Grazing livestock may pull some grass out of the roots, but most is simply grazed upon, allowing the plant to regrow once again. Kelp is frequently grazed in subtidal kelp forests, but regrows at the base of the blade continuously to cope with browsing pressure. Animals may also be grazed upon. Female mosquitoes land on hosts briefly to gain sufficient proteins for the development of their offspring. Starfish may be grazed on, being capable of regenerating lost arms. Parasitism. Parasites can at times be difficult to distinguish from grazers. Their feeding behavior is similar in many ways, however they are noted for their close association with their host species. While a grazing species such as an elephant may travel many kilometers in a single day, grazing on many plants in the process, parasites form very close associations with their hosts, usually having only one or at most a few in their lifetime. This close living arrangement may be described by the term symbiosis, living together, but unlike mutualism, the association significantly reduces the fitness of the host. Parasitic organisms range from the macroscopic mistletoe, a parasitic plant, to microscopic internal parasites such as cholera. Some species, however, have more loose associations with their hosts. Lepidoptera butterfly and moth larvae may feed parasitically on only a single plant, or they may graze on several nearby plants. It is therefore wise to treat this classification system as a continuum rather than four isolated forms. Parasitoidism. Parasitoids are organisms living in or on their host and feeding directly upon it, eventually leading to its death. They are much like parasites in their close symbiotic relationship with their host or hosts. Like the previous two classifications, parasitoid predators do not kill their hosts instantly. However, unlike parasites, they are very similar to true predators in that the fate of their prey is quite inevitably death. A well-known example of parasitoids are the ichneumon wasps, solitary insects living a free life as an adult, then laying eggs on another species such as a caterpillar. Its larvae feed on the grown host, causing it little harm at first, but soon devouring the internal organs until finally destroying the nervous system, resulting in prey death. By this stage, the young wasps are developed sufficiently to move to the next stage in their life cycle. Though limited mainly to the insect order Hymenoptera, parasitoids make up as much as 10% of all insect species. Degree of specialization. Among predators, there is a large degree of specialization. Many predators specialize in hunting only one species of prey. Others are more opportunistic and will kill and eat almost anything. Examples: humans, leopards, and dogs. The specialists are usually particularly well suited to capturing their preferred prey. The prey, in turn, are often equally suited to escape that predator. This is called an evolutionary arms race and tends to keep the populations of both species in equilibrium. Some predators specialize in certain classes of prey, not just single species. Almost all will switch to other prey with varying degrees of success when the preferred target is extremely scarce, and they may also resort to scavenging or herbivorous diet if possible. Trophic level. Predators are often another organism's prey, and likewise prey are often predators. Though blue jays prey on insects, they may in turn be prey for cats and snakes, which may themselves be the prey of hawks. One way of classifying predators is by trophic level. Organisms which feed on autotrophs, the producers of the trophic pyramid, are known as herbivores or primary consumers. Those that feed on heterotrophs such as animals are known as secondary consumers. Secondary consumers are a type of carnivore, but there are also tertiary consumers eating these carnivores, quaternary consumers eating them, and so forth. Because only a fraction of energy is passed on to the next level, this hierarchy of predation must end somewhere, and very seldom goes higher than 5 or 6 levels, and may go only as high as 3 trophic levels. For example, a lion that preys upon large herbivores such as wildebeest, which in turn eat grasses. A predator at the top of any food chain, that is, one that is preyed upon by no organism, is called an apex predator. Examples include the orca, tiger, and crocodile, and even omnivorous humans and American black bears. An apex predator in one environment may not retain this position if introduced to another habitat, such as dogs among alligators. Many organisms, of which humans are prime examples, eat from multiple levels of the food chain and thus make this classification problematic. A carnivore may eat both secondary and tertiary consumers, and its prey may itself be difficult to classify for similar reasons. Organisms showing both carnivore and herbivore are known as omnivores. Even supposedly strict herbivores may supplement their diet with meat. Carnivorous plants would be very difficult to fit into this classification, producing their own food but also digesting anything that they may trap. Organisms which eat detritivores or parasites would also be difficult to classify by such a scheme. Predation is competition. An alternative view offered by Richard Dawkins is that predation is a form of competition. The genes of both the predator and prey are competing for the body or survival machine of the prey organism. This is best understood in the context of the gene-centered view of evolution. Ecological role. Predators may increase the biodiversity of communities by preventing a single species from becoming dominant. Such predators are known as keystone species and may have a profound influence on the balance of organisms in a particular ecosystem. Introduction or removal of this predator, or changes in its population density, can have drastic cascading effects on the equilibrium of many other population ecosystems. For example, grazers of the grassland may prevent a single dominant species from taking over. The elimination of wolves from Yellowstone National Park had profound impacts on the trophic pyramid. Without predation, herbivores began to overgraze many woody species, affecting the area's plant populations. Additionally, wolves often kept animals from grazing in riparian areas, which protected beavers from having their food sources encroached upon. The removal of wolves had a direct effect on beaver populations, as their habitat became territory for grazing. Adaptations and behavior. The act of predation can be broken down into a maximum of 4 stages: detection of prey, attack, capture, and finally consumption. The relationship between predator and prey is one which is typically beneficial to the predator and detrimental to the prey species. Sometimes, however, predation has indirect benefits to the prey species, though the individuals preyed upon themselves do not benefit. This means that, at each applicable stage, predator and prey species are in an evolutionary arms race to maximize their respective abilities to obtain food or avoid being eaten. This interaction has resulted in a vast array of adaptations in both groups. General, one adaptation helping both predators and prey avoid detection is camouflage, a form of crypsis where species have an appearance which helps them blend into the background. Camouflage consists of not only color, but also shape and pattern. The background upon which the organism is seen can be both its environment, e.g. the praying mantis to the right resembling dead leaves, other organisms, e.g. zebras, stripes blend in with each other in a herd, making it difficult for lions to focus on a single target. The more convincing camouflage is, the more likely it is that the organism will go unseen. Mimicry is a related phenomenon where an organism has a similar appearance to another species. One such example is the dronefly, which looks a lot like a bee, yet is completely harmless as it cannot sting at all. Another example of Vestigian mimicry is the eomoth, Automeris eo, which has markings on its wings which resemble an owl's eyes. When an insectivorous predator disturbs the moth, it reveals its hind wings, temporarily startling the predator and giving it time to escape. Predators may also use mimicry to lure their prey, however. Female fireflies of the genus Photorus, for example, copy the light signals of other species, thereby attracting male fireflies which are then captured and eaten. Predator. While successful predation results in a gain of energy, hunting invariably involves energetic costs as well. When hunger is not an issue, most predators will generally not seek to attack prey since the costs outweigh the benefits. For instance, a large predatory fish like a shark that is well fed in an aquarium will typically ignore the smaller fish swimming around it, while the prey fish take advantage of the fact that the apex predator is apparently uninterested. Surplus killing represents a deviation from this type of behavior. The treatment of consumption in terms of cost-benefit analysis is known as optimal foraging theory and has been quite successful in the study of animal behavior. Costs and benefits are generally considered an energy gain per unit time, though other factors are also important, such as essential nutrients that have no caloric value but are necessary for survival and health. Size-selective predation involves predators preferring prey of a certain size. Large prey may prove troublesome for a predator, while small prey might prove hard to find and in any case provide less of a reward. This has led to a correlation between the size of predators and their prey. Size may also act as a refuge for large prey. For example, adult elephants are generally safe from predation by lions, but juveniles are vulnerable. It has been observed that well-fed predator animals in lax captivity, for instance, cattle farm animals will usually differentiate between putative prey animals who are familiar co-inhabitants in the same human area from wild ones outside the area. This interaction can range from peaceful coexistence to close companionship. Motivation to ignore the predatory instinct may result from mutual advantage or fear of reprisal from humans masters who have made clear that harming co-inhabitants will not be tolerated. Pet cats and pet mice, for example, may live together in the same human residence without incident as companions. Pet cats and pet dogs under human mastership often depend on each other for warmth, companionship, and even protection, particularly in rural areas. Anti-predator adaptations. Anti-predator adaptations have evolved in prey populations due to the selective pressures of predation over long periods of time. Aggression. Animals themselves predatory often use their usual methods of attacking prey, often claws and teeth, to inflict or threaten to inflict grievous injury upon potential predators. Such makes a rattlesnake or a badger less than desirable prey item. Many prey creatures not themselves predatory, such as a zebra, can give one of its usual predators, such as a lion or a spotted hyena, a strong kick that can break the jaw of its enemy and cause eventual starvation. Mobbing behavior. Mobbing behavior occurs when a species turns the tables on their predator by cooperatively attacking or harassing it. This is most frequently seen in birds, though it is also known to occur in other social animals. For example, nesting gull colonies are widely seen to attack intruders, including humans. Costs of mobbing behavior include the risk of engaging with predators, as well as energy expended in the process. Mockingbirds can effectively force a cat or dog to seek something less troublesome. One mockingbird might fly in front of the cat or dog, enticing it to lunge, while another pecks at the cat or dog from behind. While mobbing has evolved independently in many species, it only tends to be present in those whose young are frequently preyed on, especially birds. It may complement cryptic behavior in the offspring themselves, such as camouflage and hiding. Mobbing calls may be made prior to or during engagement in harassment. Mobbing behavior has functions beyond driving the predator away. Mobbing draws attention to the predator, making stealth attacks impossible. Mobbing also plays a critical role in the identification of predators and intergenerational learning about predator identification. Reintroduction of species is often unsuccessful because the established population lacks this cultural. Reintroduction of species is often unsuccessful because the established population lacks this cultural knowledge of how to identify local predators. Scientists are exploring ways to train populations to identify and respond to predators before releasing them into the wild. Mobbing can be an interspecies activity. It is common for birds to respond to mobbing calls of a different species. Many birds will show up at the site of mobbing and watch and call, but not participate. It should also be noted that some species can be on both ends of a mobbing attack. Crows are frequently mobbed by smaller songbirds as they prey on eggs and young from these birds' nests, but these same crows will cooperate with smaller birds to drive away hawks or larger mammalian predators. On occasion, birds will mob animals that pose no threat. Black-headed gulls are one species which aggressively engages intruding predators, such as carrion crows. Experiments on this species by Hans Krug involve placing hen eggs at intervals from a nesting colony and recording the percentage of successful predation events as well as the probability of the crow being subjected to mobbing. The results showed decreasing mobbing with increased distance from the nest, which was correlated with increased predation success. Mobbing may function by reducing the predator's ability to locate nests, as predators cannot focus on locating eggs while they are under direct attack. Advertising unprofitability. Once a predator has detected its prey, one would expect it to pursue it. However, it is not always profitable for the predator to do so. Consider the example of a Thomson's gazelle being spotted predator. Giving chase to prey requires a sacrifice in energy. If, however, there is some way the prey species can convey the information that it is unprofitable, energy will be saved by both organisms. Thomson's gazelles are hunted by species such as lions and cheetahs. When they see the predator approach, they may start to run away, but then slow down and stop. Stunning describes a behavior involving jumping into the air with the legs kept straight and stiff, and the white rear fully visible. Obviously, this behavior is maladaptive if they hope to outrun the predator, so it must serve some other purpose. Although other hypotheses have been put forward, evidence supports the proposition that they sought to signal an unprofitable chase. For example, cheetahs abandon more hunts when the gazelle stoats, and in the event they do give chase, they are far less likely to make a kill. Aposematism, where organisms are brightly colored as a warning to predators, is the antithesis of camouflage. Some organisms pose a threat to their predators, for example they may be poisonous, or able to harm them physically. Aposematic coloring involves bright, easily recognizable and unique colors and patterns. Upon being harmed, e.g. stung, by their prey, the appearance in such an organism will be remembered as something to avoid. Population dynamics. It is fairly clear that predators tend to lower the survival and fecundity of their prey, but on a higher level of organization, populations of predator and prey species also interact. It is obvious that predators depend on prey for survival, and this is reflected in predator populations being affected by changes in prey populations. It is not so obvious, however, that predators affect prey populations. Eating a prey organism may simply make room for another if the prey population is approaching its carrying capacity. The population dynamics of predator-prey interactions can be modeled using the Leckville-Terra equations. These provide a mathematical model for the cycling of predator and prey populations. Evolution of predation. Predation appears to have become a major selection pressure shortly before the Cambrian period around 550 million years ago, as evidenced by the almost simultaneous development of calcification in animals and algae, and predation avoiding burrowing. However, predators have been grazing on microorganisms since at least 1,000 million years ago. Humans and predation. In conservation, predators are an important consideration in matters relating to conservation. Introduced predators may prove too much for populations which have not co-evolved with them, leading to possible extinction. This will depend largely on how well the prey species can adapt to the new species, and whether or not the predator can turn to alternative food sources when prey populations fall to minimal levels. If a predator can use an alternative prey instead, it may shift its diet towards that species in a behavior known as functional response, while still eating the last remaining prey organisms. On the other hand, the prey species may be able to survive if the predator has no alternative prey. In this case, its population will necessarily crash following the decline in prey, allowing some small proportion of prey to survive. Introduction of an alternative prey may well lead to the extinction of prey, as this constraint is removed. Predators are often the species endangered themselves, especially apex predators who are often in competition with humans. Competition for prey from other species could prove the end of a predator if their ecological niche overlaps completely with that of another. The competitive exclusion principle requires only one can survive. Loss of prey species may lead to co-extinction of their predator. In addition, because predators are found in higher trophic levels, they are less abundant and much more vulnerable to extinction. Biological pest control. Predators may be put to use in conservation efforts to control introduced species. Although the aim in this situation is to remove the introduced species entirely, keeping its abundance down is often the only possibility. Predators from its natural range may be introduced to control populations, though in some cases this has little effect and may even cause unforeseen problems. Besides their use in conservation biology, predators are also important for controlling pests in agriculture. Natural predators are an environmentally friendly and sustainable way of reducing damage to crops, and are one alternative to the use of chemical agents such as pesticides. D4. Symbiosis. The term symbiosis, from the Greek, syn, with, and biosis, living, commonly describes close and often long-term interactions between different biological species. The term was first used in 1879 by the German mycologist Heinrich Anton de Berry, who defined it as the living together of unlike organisms. The definition of symbiosis is in flux and the term has been applied to a wide range of biological interactions. The symbiotic relationship may be categorized as being mutualistic, parasitic, or commensal in nature. Others define it more narrowly as only those relationships from which both organisms benefit, in which case it would be synonymous with mutualism. Symbiotic relationships include those associations in which one organism lives on another active symbiosis, such as mistletoe, or where one partner lives inside another endosymbiosis, such as lactobacilli and other bacteria and humans or zooxanthellae and corals. Symbiotic relationships may be either obligate, i.e., necessary to the survival of at least one of the organisms involved, or facultative, where the relationship is beneficial but not essential to survival of the organisms. Physical interaction. Endosymbiosis is any symbiotic relationship in which a symbiote lives within the tissues of the host, either in the intercellular space or extracellularly. Examples are nitrogen-fixing bacteria called rhizobia, which live in root nodules on legume roots, actinomycete nitrogen bacteria called frankia, which live in alder tree root nodules, single-celled algae inside reef-building corals, and bacterial endosymbionts that provide essential nutrients to about 10%-15% of insects. Ectosymbiosis, also referred to as exosymbiosis, is any symbiotic relationship in which a symbiont lives on the body surface of the host, including the inner surface of the digestive tract or the ducts of exocrine glands. Examples of this include ectoparasites such as lice, commensal ectosymbionts, such as the barnacles that attach themselves to the jaw of baleen whales, and mutualist ectosymbionts such as cleaner fish. Mutualism. Mutualism is a biological interaction between individuals of two different species, where both individuals derive a fitness benefit, for example increased survivorship. Similar interactions within a species are known as cooperation. It can be contrasted with interspecific competition, in which both species experience reduced fitness, and exploitation, in which one species benefits at the expense of the other. Mutualism and symbiosis are sometimes used as if they are synonymous, but this is strictly incorrect. Symbiosis is a broad category, defined to include relationships which are mutualistic, parasitic, or commensal. Mutualism is therefore only one type. Mutualism plays a key part in ecology and evolutionary biology. For example, mutualistic interactions are vital for terrestrial ecosystem function as more than 70% of land plants rely on mycorrhizal relationships with fungi to provide them with inorganic compounds and trace elements. In addition, mutualism has driven the evolution of much of the biological diversity we see, such as flower forms important for pollination mutualisms and coevolution between groups of species. However, mutualism has historically received less attention than other interactions such as predation and parasitism. Measuring the exact fitness benefit to the individuals is not always straightforward, particularly when the individuals can receive benefits from a range of species, for example most plant pollinator mutualisms. It is therefore common to categorize mutualisms according to the closeness of the association, using terms such as obligate versus facultative. Defining closeness, however, is also problematical. It can refer to mutual dependency. The species cannot live without one another, or the biological intimacy of a relationship in relation to physical closeness, e.g. one species living within the tissues of the other species. Types of relationships. Mutualistic interactions can be thought of as a form of biological barter, in which species trade resources, for example carbohydrates or inorganic compounds, or services such as gamete, offspring dispersal, or protection from predators. Resource-resource relationships. Resource-resource interactions, in which one type of resource is traded for a different resource, are probably the most common form of mutualism. For example, mycorrhizal associations between plant roots and fungi, with the plant providing carbohydrates to the fungus in return for primarily phosphate but also nitrogenous compounds. Other examples include rhizobia bacteria, which fix nitrogen for leguminous plants, family Fabaceae, in return for energy-containing carbohydrates. Service-resource relationships. Service-resource relationships are also common. For example, pollination, in which nectar of pollen food resources are traded for pollen dispersal, a service for and protection of aphids, where the aphids trade sugar-rich honeydew, a byproduct of their mode of feeding on plant sap, in return for defense against predators such as ladybird beetles. Service-service relationships. Strict service-service interactions are very rare, for reasons that are far from clear. One example is the relationship between sea anemones and animalfish in the family Comacentridae. The anemones provide the fish with protection from predators, which cannot tolerate the stings of the anemone's tentacles, and the fish defend the anemones against butterfly fish family Chaetodontidae, which eat anemones. However, in common with many mutualisms, there is more than one aspect to the biological barter. In the animalfish anemone mutualism, waste ammonia from the fish feed the symbiotic algae that are found in the anemone's tentacles. Therefore, what appears to be a service-service mutualism in fact has a service-resource component. A second example is that of the relationship between some ants and trees in the genus Acacia, such as the whistling thorn and bullhorn acacia. The ants nest inside the plant's thorns. In exchange for shelter, the ants protect acacias from attack by herbivores, which they frequently eat, introducing a resource component to this service-service relationship, and competition from other plants by trimming back vegetation that would shade the acacia. In addition, another service-resource component is present, as the ants regularly feed on lipid-rich food bodies called Bölgian bodies that are on the acacia plant. Humans and mutualism. Humans also engage in mutualisms with other species, including our gut flora, without which we would not be able to digest food efficiently, and domesticated animals such as horses, which provide transportation in return for food and shelter. In traditional agriculture, many plants will function mutualistically as companion plants, providing each other with shelter, soil fertility, and repelling of pests. For example, beans may grow up corn stalks as a trellis, while fixing nitrogen in the soil for the corn, as exploited in the Three Sisters gardening technique. The question how and why species might cooperate has been addressed philosophically by a number of writers. Giles Deleuze, for example, was interested in the way this questioned the conception of evolutionism and the notion of linear historical progress. A large percentage of herbivores have mutualistic gut fauna that help them digest plant matter, which is more difficult to digest than animal prey. Coral reefs are the result of mutualisms between coral organisms and various types of algae that live inside them. Most land plants and land ecosystems rely on mutualisms between the plants which fix carbon from the air, and mycorrhizal fungi which help in extracting minerals from the ground. Another example is the goby fish, which sometimes lives together with a shrimp. The shrimp digs and cleans up a burrow in the sand in which both the shrimp and the goby fish live. The shrimp is almost blind, leaving it vulnerable to predators when above ground. In case of danger, the goby fish touches the shrimp with its tail to warn it. When that happens, both the shrimp and goby fish quickly retract into the burrow. One of the most spectacular examples of obligate mutualism is between the sibilant tube worms and symbiotic bacteria that live at hydrothermal vents and cold seeps. The worm has no digestive tract and is solely reliant on their internal symbionts for nutrition. The bacteria oxidize either hydrogen sulfide or methane which the host supplies to them. These worms were discovered in the late 1980s at the hydrothermal vents near the Galapagos Islands and have since been found at deep sea hydrothermal vents and cold seeps in all of the world's oceans. Symbiosis and evolution. While historically, symbiosis has received less attention than other interactions such as predation or competition, it is increasingly recognized as an important selective force behind evolution, with many species having a long history of interdependent coevolution. In fact, the evolution of all eukaryotes, plants, animals, fungi, protists is believed to have resulted from symbiosis between various sorts of bacteria. Symbiogenesis. The biologist Lynn Margulis, famous for the work on endosymbiosis, contends that symbiosis is a major driving force behind evolution. She considers Darwin's notion of evolution, driven by competition, as incomplete, and claims evolution is strongly based on cooperation, interaction, and mutual dependence among organisms. According to Margulis and Dorian Sagan, life did not take over the globe by combat, but by networking. Coevolution. Symbiosis played a major role in the coevolution of flowering plants and the animals that pollinate them. Many plants that are pollinated by insects, bats or birds, have very specialized flowers modified to promote pollination by a specific pollinator that is also correspondingly adapted. The first flowering plants in the fossil record had relatively simple flowers. Adaptive speciation quickly gave rise to many diverse groups of plants, and at the same time, corresponding speciation occurred in certain insect groups. Some groups of plants developed nectar and large sticky pollen, while insects evolved more specialized morphologies to access and collect these rich food sources. In some taxa of plants and insects, the relationship has become dependent. 32, where the plant species can only be pollinated by one species of insect. Biotic pollination, a best example of mutualism. Pollination in angiosperms and gymnosperms is the process that transfers pollen grains, which contain the male gamete sperm, to where the female gametes are contained within the carpel. In gymnosperms, the pollen is directly applied to the ovule itself. The study of pollination brings together many disciplines, such as botany, horticulture, entomology, and ecology. Pollination is a necessary step in the sexual reproduction of flowering plants, resulting in the production of offspring that are genetically diverse. It is important in horticulture and agriculture because fruiting is dependent on fertilization, which is the end result of pollination. Types. The process of pollination requires pollinators, agents that carry or move the pollen grains from the anther to the receptive part of the carpel or pistil. The receptive part of the carpel is called the stigma in the flowers of angiosperms. The receptive part of the gymnosperm ovule is called the micropyle. The various flower traits that attract different pollinators are known as pollination syndromes. Methods of pollination with common pollinators or plants are: biotic pollination occurs when pollination is mediated by an organism termed a pollinator. There are roughly 200,000 varieties of animal pollinators in the wild, most of which are insects. Entomophily, pollination by insects, often occurs on plants that have developed blue petals and a strong scent to attract insects such as bees, wasps, and occasionally ants, Hymenoptera, beetles, Coleoptera, moths and butterflies, Lepidoptera, and flies, Diptera. In zoophily, pollination is done by vertebrates such as birds and bats, particularly hummingbirds, sunbirds, spider hunters, honeyeaters, and fruit bats. Pollinators and pollinizers. Pollination also requires consideration of pollinizers. The terms pollinator and pollinizer are often confused. A pollinator is the agent that moves the pollen, whether it be wind, bees, bats, moths, or birds. A pollinizer is a plant that provides the pollen. Some plants are self-fertile or self-compatible and can pollinate themselves. Other plants have chemical or physical barriers to self-pollination and need to be cross-pollinated. With these self-infertile plants, not only pollinators must be considered but pollinizers as well. In pollination management, a good pollinizer is a plant that provides compatible, viable, and plentiful pollen and blooms at the same time as the plant that is to be pollinated. Pollination can be cross-pollination with a pollinator and external pollinizer, self-pollination with a pollinator, or self-pollination without any pollinator. Cross-pollination syngony, pollen is delivered to a flower of a different plant. Plants adapted to outcross or cross-pollinize have taller stamens and carpels to better spread pollen to other flowers. Self-pollination, autogamy, pollen moves to the female part of the same flower or to another flower on the same individual plant. This is sometimes referred to as self-pollination, but this is not synonymous with autogamy. Clarity requires that the term self-pollination be restricted to those plants that accomplish pollination without an external pollinator. Example: the stamens actually grow into contact with the pistil to transfer the pollen. Most peach varieties are autogamous, but not truly self-pollinated, as it is generally an insect pollinator that moves the pollen from anther to stigma. Plants adapted to self-fertilize have similar stamen and carpel length. Cleistogamy, pollination that occurs before the flower opens is always self-pollination. Some cleistogamous flowers never open, in contrast to chastogamy flowers that open and are then pollinated. Cleistogamous flowers must of necessity be self-compatible or self-fertile plants. Other plants are self-incompatible. These are endpoints on a continuum, not absolute points. Hybridization is effective pollination between flowers of different species of the same genus, or even between flowers of different genera, as in the case of several orchids. Peaches are considered self-fertile because a commercial crop can be produced without cross-pollination, though cross-pollination usually gives a better crop. Apples are considered self-incompatible because a commercial crop must be cross-pollinated. Remember that most fruits are grafted clones, genetically identical. An orchard block of apples of one variety is in effect all one plant. Growers now consider this a mistake. One means of correcting this mistake is to graft a limb of an appropriate pollinizer, generally a variety of crabapple, every 6 trees or so. Commensalism. In ecology, commensalism. An orchard block of apples of one variety is in effect all one plant. Growers now consider this a mistake. An orchard block of apples of one variety is in effect all one plant. Growers now consider this a mistake. One means of correcting this mistake is to graft a limb of an appropriate pollinizer, generally a variety of crabapple, every 6 trees or so. Commensum. In ecology, commensalism. In ecology, commensalism is a kind of symbiotic relationship between two organisms where one benefits and the other is not significantly harmed or helped, like a bird living in a tree. The term derives from the English word commensal, meaning sharing of food. In human social interaction, that word derives from the Latin commensa, meaning sharing a table. Types. As with all ecological interactions, commensalisms vary in strength and duration from intimate, long-lived symbiosis to brief, weak interactions through intermediaries. It is one of the 3 kinds of symbiotic relationships. Originally, it was used to describe the use of waste food by second animals, like the carcass eaters that follow hunting animals but wait until they have finished their meal. Other forms of commensalism include 4c. One animal attaching to another animal for transportation only. This concerns mainly arthropods, examples of which are mites on insects, such as beetles, flies, or bees, pseudoscorpions on mammals, and millipedes on birds. 4c can be either obligated or facultative, induced by environmental conditions. Inquilinism, using a second organism for housing. Examples are epiphytic plants, such as many orchids, which grow on trees, or birds that live in holes in trees. Metabiosis, a more indirect dependency, in which the second organism uses something the first created, however after the death of the first. An example is the hermit crabs that use gastropod shells to protect their bodies. The question of whether the relationship between humans and some types of alga flora is commensal or mutualistic is still unanswered. Some biologists argue that any close interaction between two organisms is unlikely to be completely neutral for either party, and that relationships identified as commensal are likely mutualistic or parasitic in a subtle way that has not been detected. For example, epiphytes are nutritional pirates that may intercept substantial amounts of mineral nutrients that would otherwise go to the host plant. Large numbers of epiphytes can also cause tree limbs to break or shade the host plant and reduce its rate of photosynthesis. Similarly, the phoronic mites in the image above may hinder the host by making flight more difficult, which may affect its aerial hunting ability or cause it to expend extra energy while carrying these passengers. Parasitism. Parasitism is a type of symbiotic relationship between organisms of different species in which one, the parasite, benefits from a prolonged, close association with the other, the host, which is harmed. In general, parasites are much smaller than their hosts, show a high degree of specialization for the mode of life and reproduce more quickly and in greater numbers than their hosts. Classic examples of parasitism include the interactions between vertebrate hosts and such diverse animals as the tapeworms, flukes, plasmodium species, and fleas. The harm and benefit in parasitic interactions concern the biological fitness of the organisms involved. Parasites reduce host fitness in many ways, ranging from general or specialized pathology, such as castration and impairment of secondary sex characteristics, to the modification of host behavior. Parasites increase their fitness by exploiting hosts for food, habitat, and dispersal. Although the concept of parasitism applies unambiguously to many cases in nature, it is best considered part of a continuum of types of interactions between species, rather than an exclusive category. Particular interactions between species may satisfy some but not all parts of the definition. In many cases, it is difficult to demonstrate that the host is harmed. In others, there may be no apparent specialization on the part of the parasite, or the interaction between the organisms may be short-lived. In medicine, only eukaryotic organisms are considered parasites, to the exclusion of bacteria and viruses. Some branches of biology, however, do regard members of these groups to be parasitic. Types of parasitism. Parasites are classified based on a variety of aspects of their interactions with their hosts and on their life cycles. Those that live inside the host are called endoparasites, e.g., hookworms, and those that live on its surface are called ectoparasites, e.g., some mites. An epiparasite is one that feeds on another parasite. This relationship is also sometimes referred to as hyperparasitism. Parasitoids are organisms that cause the host to die as a result of parasitism. Thus, the interaction between the parasitoid and the host is fundamentally different than true parasites and their host, and shares some characteristics with predation. Social parasites take advantage of interactions between members of social organisms such as ants or termites. In kleptoparasitism, parasites appropriate food gathered by the host. An example is the brood parasitism practiced by many species of cuckoo. Many cuckoos use other bird species as babysitters, depositing their eggs in the nest of the host species, which raise the cuckoo young as one of their own. Parasitism can take the form of isolated cheating or exploitation among more generalized mutualistic interactions. For example, broad classes of plants and fungi exchange carbon and nutrients in common mutualistic mycorrhizal relationships. However, a few plant species known as mycoheterotrophs cheat by taking carbon from a fungus rather than donating it. Evolutionary aspects. Biotrophic parasitism is an extremely common mode of life that has arisen independently many times in the course of evolution. Depending on the definition used, as many as half of all animals have at least one parasitic phase in their life cycles, and it is also frequent in plants and fungi. Moreover, almost all free living animals are host to one or more parasite taxa. Parasites evolve in response to defense mechanisms of their hosts. Examples of host defenses include the toxins produced by plants to deter parasitic fungi and bacteria, the complex vertebrate immune system, which can target parasites through contact with bodily fluids, and behavioral defenses. An example of the latter is the avoidance by sheep of open pastures during spring, when roundworm eggs accumulated over the previous year hatch en masse. As a result of these and other host defenses, some parasites evolve adaptations that are specific to a particular host taxon and specialized to the point where they infect only a single species. Such narrow host specificity can be costly over evolutionary time, however, if the host species becomes extinct. Thus, many parasites are capable of infecting a variety of host species that are more or less closely related, with varying success. Host defenses also evolve in response to attacks by parasites. Theoretically, parasites may have an advantage in this evolutionary arms race because of their more rapid generation time. Hosts reproduce less quickly than parasites, and therefore have fewer chances to adapt than the parasites do over a given span of time. In some cases, a parasite species may co-evolve with its host taxa. In theory, long-term coevolution should lead to a relatively stable relationship tending to commensalism or mutualism, in that it is in the evolutionary interest of the parasite that its host thrives. A parasite may evolve to become less harmful for its host, or a host may evolve to cope with the unavoidable presence of the parasite to the point that the parasite's absence causes the host harm. For example, although animals infected with parasitic worms are often clearly harmed, and therefore parasitized, such infections may also reduce the prevalence and effects of autoimmune disorders in animal hosts, including humans. The presumption of a shared evolutionary history between parasites and hosts can sometimes elucidate how host taxa are related. The presumption of a shared evolutionary history between parasites and hosts can sometimes elucidate how host taxa are related. For instance, there has been dispute about whether flamingos are more closely related to the storks and their allies or to ducks, geese and their relatives. The fact that flamingos share parasites with ducks and geese is evidence these groups may be more closely related to each other than either is to storks. Parasitism is part of one explanation for the evolution of secondary sex characteristics seen in breeding males throughout the animal world, such as the plumage of male peacocks and manes of male lions. According to this theory, female hosts select males for breeding based on such characteristics because they indicate resistance to parasites and other disease. E-community ecology. 1. Concept. Community, an association of interacting populations, usually defined by the nature of their interaction or the place in which they live. Community can be used in a more limited sense, such as the plant community, animal community, or even the bird community, the insect community, etc. Holistic concept, the view that communities are superorganisms that can only be understood as host clements. Individualistic concept, the idea that communities are merely functions of populations and are not organized in any way. Gleason. Most ecologists today are between these two extremes. Keystone species, a species which influences the entire community so much that its removal will cause ecosystem collapse, can be a keystone predator. 2. Characteristics of a community. Like a population, a community too has its own characteristics, which are not shown by its individual component species. These characteristics, which have meaning only with reference to community level organization, are as follows. Species diversity. Each community is made up of much different organisms, plants, animals, microbes, which differ taxonomically from each other. The number of species and population abundance in community also vary greatly.